Hello and welcome to the Wednesday, November 29th online class video. Now it's a little circular, but I'll have a link to this video also in here. There are answers and there are going to be questions in Top Hat that are open. Once this is released, please answer those by tomorrow at midnight. I'm sorry I couldn't get this video out during our normal scheduled class time. So I'm giving you more time on the questions because I know you have a lot going on. All right, there are optional problems on Connect that somebody requested for me that I allow for study attempts or something like that. I don't remember why, but the only way Connect will let me do it is if I put in a due date. And at the time I thought I was doing something way in the future, but anyway, now I guess some people thought that these problems were actually due and they're not. So I took off the due date and changed some other settings. Hopefully I don't mess anybody up. Okay, there is a new regression analysis assignment number 2, and it is, here's the link to it, and it is due Monday evening as a soft deadline and Tuesday the 5th as a hard deadline. So I am going to be talking today about the skills basically that you need to know to do that assignment. Okay. Okay, so we're going to go into the learning objective is interpret goodness of fit measures, but really this is the section where we're doing model selection. And I personally think that not only is it wrong, I think it's wrong to teach it wrong. The book is just taking you guys down what I think would be some very bad habits if you were ever going to do linear regression analysis, which you hopefully will. So I want to go through what is kind of considered the more basic fundamental approach. So you start out by identifying a numerical response variable. Now, there are ways that are a little more advanced for doing a categorical response variable, but we're not going to have time to get to them this semester. And then you want to identify from your data all the reasonable predictors. So you want to use ones that make economic and intuitive sense. Obviously, you could probably think of things that you don't have data for, which is, not so helpful. You can, unless you're planning a study. But anyway, you have to work with what you got. Then you're going to run correlations and scatter plots. Now, those of you who did the regression analysis assignment 1 already did this. But now I'm adding something, and contingency tables for categorical variables. And we're going to go over that here in a minute. But basically, you want to find out which numerical predictors are linearly related to the response variable and which dummy variables appear predictive of response. All right, so going back to that college scorecard data that we started to look at, we're going to want to go in and identify which are those predictors here. So let's go back over. Well, actually, I think I'm going to save time and not do this with you guys. You guys should know how to do this. So I ran correlations with earnings being the response variable. So I find it easier to interpret. It's actually very helpful to interpret if earnings is the first column of data when you run a correlation in a grid like this. And we look for where are the correlations that are greater than 0.15. So we have a pretty low bar on this because sometimes you can get improved model fitting through including predictors that are only mildly correlated. So anyway, we start out by having our candidate predictors, and notice that the city, which is 1, 0, is binary. You could say, well, isn't that numerical? So, binary kind of is in its weird little category, but it's coming from a categorical. So I'm going to treat it like a value of categorical, and I'll show you that in a minute. But anyway, so I want to kind of run, you know, I always told you when we were learning about correlations that you can't just trust these numbers. These numbers all are kind of moderate, but you always want to run a scatter plot to see if they are actually linearly related. So we see that cost appears to be and grad rate appears to be, but debt is a little questionable. You can kind of see there's a smear up over here where the points almost look like it's an exponential growth, if you will. So I just put a question mark there, and I'm going to kind of try a little bit to follow the book and include it for now, but we'll see where this is going. Okay. So then the next thing is you're going to look at any possible categorical variables, and you're going to create a contingency table. All right. So what's really important when you do this is that you're going to have your, let me see if I can get an annotation on here. You're going to have your average of the response variable for every value of the categorical variable. So city has 0, 1. If it was eye color, it would be blue, brown, hazel, green, or something. But you definitely want average here. And remember that when you run this in Excel, it's going to default to sum. Don't do sum because sum is very misleading. So you've got to change it to average by doing the value field settings. So let me just go over that real quick with you guys. And then there's a little bit of another gotcha if you're using a 0, 1 dummy variable. So let me just go through creating this right here. Okay, so I'm going to go, oops, I think I forgot to open it. I'm going to pause a second. Okay, so here's that college worksheet that we were working with in class on Monday. And what I want to do is put together a pivot table to do this contingency table. So I could just do earnings and city, but why not just put it all in? It's quicker and easier. So I'm going to use the shift and control or command down arrow key so I don't have all my blanks in my pivot table. All right, then I'm going to go to insert pivot table and we'll go to an existing worksheet and I'm just going to put it, oops, underneath where those scatter plots were. And I'll just add it right here. All right, so this is what we're going to use. If you have more than one categorical variable, you're going to want to check each one versus the average of the response variable. All right, so let's click in here. We only have one, which city. We're going to treat binomial 0, 1 binary, variables as categorical. All right, so we'll put city in here, and then we're going to bring down the response variable. So we put it into values, and you see it gives you sum, which we don't want. You're going to hit that value field settings, and really this should be the default. I don't know why Excel doesn't have it as a default, but then we'll get the average in there. All right, so now that we have this average, I'm going to copy it. You guys know this routine, and paste the values. And so I can edit this table and format it and do nice what I want for charts. So first thing I'm going to do is I'm going to write this as city. Now here's the catch with 0, 1 dummy type variables. You need to actually rename them because Excel doesn't know how to graph them. So I'm going to say not in a city because that's what 0 meant. And then I'm going to do city. So I'm actually writing out words instead of a number there. All right, so the rest of this, let's just quickly format it. You guys know how to do all this, so I'm not going to spend a ton of time here. I'm just going to, and obviously once we have this set up, if you had more than one categorical variable, you could do this for that other categorical variable. Okay, I actually prefer, let's see, okay. Now we're going to take these, let's grab the headers and leave off the grand total and insert a column. bar chart. If you happen to have a Windows computer, you can go up here to change chart type and it gives you a color automatically. It might be a good idea to add the data labels here as well and a legend. So we can see not in city and in the city. And so we do see that there appears to be around a $4,000 difference in the first year earnings. So we'll consider that significant enough that we would want to include that as a predictor. Okay. All right. So we're going to start with what's called the full model. And that means once we've identified all the predictors in our data that we think are logically, or as what I say, economic and intuitively make sense, and also show up in the data as possibly being correlated or the value, one of the values of the predictor really of a categorical value really seems to indicate a connection with the response variable. So then we're going to do an approach called a step down approach. And this is the most basic way to find a final model. The goal really is to try to identify the best model, but also the simplest model. So based on the principle of parsimony, which is that we don't want anything more complicated than it needs to be, the full model, we will start removing predictors as the idea and try to find the preferred model. What we're going to do is check a couple things, and I'm going to explain what they are. We're going to check the overall significance of the joint predictors and make sure it's significant. Usually we do defer to a 5% alpha here. And then we're also going to look at individual p-values, and I'm going to explain where all that, why that all makes sense here. In a sec, we're going to drop the one with the largest p-value that is greater than 0.05. Okay, so there's many other approaches that have been developed in more recent years for finding the best or preferred model. This is the step down approach is the oldest, most traditional one, and I think before you could even learn any others, you've got to at least know this one. So that's the one I'm teaching you. Okay, so we're going to run correlation scatter plot. We did that, and we found that we have the predictors were cost, grad, and debt, and I decided to keep in debt, even though I have a little bit of a question mark with it. Whoops. And then from the categorical contingency tables, we identified city. So the full model, which is where we're starting, is with cost, grad, debt, and city. Okay. So let's talk about some of the criteria that we have to satisfy first before we even do anything else with this model, and then how do we choose the predictor to drop and why. Okay, so consider a linear regression model with k predictor variables, right? So y equals b beta naught plus beta 1 sub 1 times x. I'm not going to read this all out. Okay, up to k. We can produce a hypothesis test about the unknown parameters. So the way we do that is where it's going to be a joint test about all of the parameters. Now, we've never seen a hypothesis test like this, and I'm not going to expect you to kind of reproduce this in a different environment. I just want you to understand the outcome of it. So, and we're also going to do individual tests about single betas, right? So for the test to be valid, we need that the different, like from different data, that the values B0, B1 up through BK have to be normally distributed. Well, mathematically, you can actually show this in reverse. You can show that if the random error term is normally distributed, by default, the sample distribution for the coefficients you get from all the different possible samples you could possibly get, and estimate all the different ones of these, will also be normally distributed. And if that is not normally distributed, then the test is valid only for large sample sizes. The test of joint significance is regarded as a test of the overall usefulness of a regression equation. This is why it's kind of the criteria. We don't want to proceed if this isn't met, because then that means we got to go throw out our data, get new data, or just do something different. So the test determines whether the predictor variables have a joint statistical influence on the response. So basically, if all the slope coefficients were to equal 0, all the predictors would drop out. There none. In other words, if you just had a big cloud in every dimension, so there's no trend. You can't see a trend. And a lot of times, by the way people see that is they hold like all the other ones constant, and then they let x1 vary, and then you maybe let everything else be held constant and let x2 vary, and look at the cloud of points in a two-dimensional space. Anyway, if everything is just a big cloud, so you say there's no correlation, kind of zero slope, then none of the predictors have a linear relationship with the response, right? But if at least one, and that should only be one at least, if at least one has a slope coefficient that does not equal 0, then at least one predictor influences the response. So the way we write that is we say, okay, beta 1 equals beta 2 all the way up to equals beta k equals 0. That's the null. And then the mathematical opposite of that isn't that they're all not equal to 0, it's just one is, because what we're saying is not only are these all equal to each other, but they're all equal to 0. So all you need is one exception for the alternative, and that's all we're going to say is if we reject the null, we're saying there's at least one. Okay, couldn't be more than one, but there's at least one that is not 0. And that's just a logical argument. There's no real math there. Okay, so and the test statistic measures how well the sample regression equation explains the variability in the response. The way we do this is we create a test statistic. So now you guys know all about test statistics. Here's a new one you haven't seen before. This is just FYI. You're not held responsible for all of this, but the K is the what's called degree of freedom 1. So there's something called an F distribution. You've learned about normal distributions and T distributions. There's a whole nother type called an F distribution, and it requires 2 degrees of freedom values to identify it, and they're given by either K or N minus K minus 1. We have seen the SSR and the SSE stuff before. So if we take the sum of the regression sum of squares divided by the K, we get what's called the mean sum of the regression mean sum. I don't know, they put the letters in the opposite direction which you say it. Anyway, so you don't have to worry about all this, okay? But you come up with this number, and I'm sure there's YouTube videos that will go through it in full detail if you're really curious. Anyway, this turns out to always be a right-tailed F test is what we end up running to do this hypothesis test. And that's because the F distribution starts at 0, so you can never be less than 0. And so what we are going to do is just get the probability of being past our test statistic, right? So let's say our F distribution looks something like this. I don't know. And then we put in our test statistic here, and we just want to find the area in the tail, right? That's our p-value. So again, hopefully this is like, yes, I know all about test, finding the area, finding a p-value, finding the area past the test statistic. And Even though I don't like all, I'm just hoping this is what you're thinking. Yeah, I don't like all this, and she's telling me I don't need to have it memorized, so thank goodness. But I do understand the concept, is what I'm hoping. So the larger test statistics provides us with more evidence to reject the null, and it indicates a larger portion of the sample variation is in the response. And by the way, what you're going to get for p-value is going to get smaller, right? So the further this goes out, the smaller the area in the tail, right? Because what you get in Excel is the area in the tail. You actually get the p-value. All right. So what you're going to see in Excel or R or most statistic packages is what's called an ANOVA table. This stands for analysis of variance. And it's because we're doing this regression sum of squares, error sum of squares, total sum of squares, and we can put together these kind of average error sum of square values, put that together into a ratio, and then we get the number. So really the only one anyone looks at very much is this one. So the significance F is the one that we're looking at or focusing on. And here's the output for running the full model that we have agreed on for the college scorecard data. And you see that you get this number, 7.56 E to the negative 13. And I thought I got this in the first time this came up, but just so you know, right, don't let this weirdness freak you out. This is just machine language for, and you might have this in your calculators. The E stands for the exponent. So this stands for times 10. It's a scientific notation to the negative 13. So what does that mean? Well, that means you take 7, 5, 6, and you take this decimal that was here and you move it 13 over. I'm not going to, pretend that I counted. And there's, you move it 13 spaces. 13 spaces. So there's 12 zeros here. So that's a really, really small number. Okay. That means that this is a very significant model jointly, which means there's at least one predictor that is highly effective, if you will. Okay. All right. So if we set up the following competing hypotheses, and in our data, we had 116 records and 4 predictors, right? That, according to everything that I showed you on that last page, ends up giving us an F of 20.868. And that's a p-value, which I just showed you is like 12 zeros and then 7. And so that's, it was a 7, right? Yeah, 756. So yeah, teeny tiny. So that's definitely smaller than an alpha of 5%. So we're going to reject the null. And so we're going to say at a 5% significance level, the predictor variables are jointly significant in explaining earnings. So that's our green light. That means, yes, okay, there's something in this data. We may not know what it is at this point, and we're going to just try to make our best guess as to what the best model looks like at predicting earnings. So let's go around down this road. Now that we talked about the joint, that we're going to talk about individual. So we're going to consider a linear regression equation with k predictors again. But now we're going to just think about one. If beta 1 were to be 0, right? If this is 0, then this whole term drops out. And we'd say there's no linear relationship between x1, whatever that predictor is, and y. So another way to say that in like plain English is that x1 does not influence y. All right. So given that, let's just like generalize this away from the specific beta 1. Let's just say beta j is some value, usually it's 0, of what, so the beta j 0 is the 0 here. Okay, it's like, what do we think that coefficient is equal to what's the slope, the influence of X on Y. And the competing hypothesis is forms together a test of individual significance. All right. So um, if these are zero, so these are normally zero, I think it's easier to think of them as zero because that's what is programmed into Excel already. But you can use this, and there's some finance um, theory that involves actually this not being zero. You might run across in your finance class. Okay, so what we're going to be saying is, okay, the null hypothesis is that that slope coefficient is zero. So the null hypothesis is that we're in the situation here. Okay, that's what this is saying. Um, that's our null, and that's, we assume it's zero. We set that to zero, which is what we do for regression analysis almost always. Then the alternative is that it's not zero, and then we want to test that. And so what we need to do is come up with a test statistic for that, right? And that test statistic hopefully looks kind of familiar to you, right? So it's the observed value, or you could say the estimated coefficient here from our regression model minus remember, this is going to be like a zero because this is the expected value from the null hypothesis. So let's just go ahead and remind ourselves that this is almost always a zero. And then over the standard error. Okay, so it's the standard error in that single estimator. All right, and it's going to follow a student's t distribution with the degrees of freedom being n minus k minus 1. So previously we'd seen a lot of n minus 1 degrees of freedom. All right. If you wanted to test about the intercept, which is rare, whether or not it's different from zero, you could do the same kind of setup. But usually we don't focus on that very much. Okay, so statistical packages like Excel's regression analysis tool, and it report the p-values for a two-tailed test, right? And they're going to always have the beta j sub zero, the specific value, be a zero. So we're testing whether the slope is different from zero. All right, so if we run the full model, we get the following coefficients. So let me just remind you, I think we have this up here. We were working on this on Monday, so recall, scroll over, and we ran the full model. So here's cost, grad, depth, and city. And I had a typo there. Okay, anyway, I'm focusing up here on the output. So remember, we built this bottom part. The output that we got from Excel was a box with regression statistics, which I'm getting ready to cover. The ANOVA we just finished. Remember, all I care about really here is the significance. And then we're going to look at the coefficients. Now we're going to start focusing on the p-values. So we're going to look at this column. Now what Excel gives you is all the information you need to build your own test statistic. To do other things. It does even build the t-test statistic for you. And then it goes ahead and gives you the two-sided p-value, or sorry, a two-tailed test. Okay, so that's what you're looking at when you look at this, right? So let's go back and make sure we know where to place each piece here. Whoops. So we have the standard errors being given to us, the actual t is calculated, and then the p-value of a two-sided, two-tailed test is calculated as well. All right, so we have all those p-values. And let's just focus on one of them, beta 1. If we can set up the following hypothesis: the null is that beta 1 is 0, and the alternative is it's not. we have an estimate of 0.4349. It had a standard error of 0.1110, and we have a degrees of freedom, right? Remember now this is n minus k minus 1. We have 4 predictors, so we have 116 records minus 4 predictors minus 1. So really 116 minus 5, or 111. And we are going to calculate that test statistic. It comes out to 3.917. We are going to look at the distribution of a student's T, and we want to find the area in the tail past the 3.917, right? So it's a two-tailed test. We're going to add that area to the area below negative 3.917, if you remember all this. And that area is the p-value that's given in Excel, which is really, really small. So we reject the null, and that means we accept the alternative. And so the alternative that we're accepting is that the slope is not 0. That doesn't mean that the slope is 0.4349. What we're saying, right, is that we just are accepting that to a significance of 5%, cost is significant in explaining earnings. It's something. And this is just a point estimate. Remember, Monday we were talking about putting a confidence interval around what it is, or maybe even a prediction interval. Well, regardless, what we're saying is it's not 0. It matters. Okay. So in this model selection steps, as we're moving through this, I've just now hopefully clarified what these 2 steps are. And those 2 steps kind of help us, because we're going to then use that to guide us. And what we're going to do is, first of all, we're going to make sure we've satisfied step 1, the criteria that it's even worth doing anything. And then we're going to look at the coefficients p-values. And remember, big p-values are bad. Small p-values are good. So we're going to drop the one with the largest p-value that's greater than 0.05. Okay, that means it's, we can't tell based on the data if the slope is different from 0, which means the predictor is not able to predict anything about the response. All right, and we drop that, and we do it one step at a time, one predictor at a time, because everything can change once you drop a predictor. All the estimates, everything will be different. We call that the reduced model, because we've taken away one predictor. And then we're going to compare how it does with the original one. We're going to compare the goodness of fit, which you, as of yet, don't know how to do that. We're going to also compare p-values of the coefficients, the new ones, the new p-values, and we're going to continue reducing the model until we have a preferred model identified. And usually down to 2 or 3 top choices. And depending on what stage you are in learning, may, at this point, we're just going to focus on a few of our top choices for kind of learning purposes. But literally, we're going to go through only 2 or 3 or 4 models. In the real world, you can go through hundreds of variations very quickly. It doesn't take that long to do any of them. Okay, so let's keep going here. Okay, so what are these goodness of fit measures? And basically, what they're going to do is just do exactly what it says. How good is the fit of that model to the data? So there's the standard error of the estimate, which is given the notation S sub E, and the coefficient of determination R squared, and the adjusted coefficient of determination, which we call the adjusted R squared. So let's get into this. The first one we're going to talk about is the standard error. Recall, a residual is a difference between the observed and the predicted value of the response, right? It's the vertical distance that the point is off the line. That's what that's saying. And we want this to be as small as possible, right? We would like we would say that the line is fitting the data very well if the errors are small. So we take and we get the error sum of squares. So we add up all those individual errors for every I, right? If you remember this, we add these up squared. So we're going to add these up, but we're going to square each difference each time. And that's our SSE. All right. And then we're going to kind of get the average of it in a sense by dividing by the degrees of freedom. And then we're going to get the square root of that whole thing. So we have units that are back in the original units of Y. All right. And again, the notation stuff we've already been talking about. So I think you're good there. For a given sample size, increasing the number of predictors reduces the numerator and denominator. I think I'm going to switch over to Top Hat. I just realized that there are questions in here that I want to stop and make sure you do. So hold on one second. Okay, pause and go answer this question on Top Hat. If the joint significance p-value, significance f, is less than 0.05, what does this imply? Does it mean all the oops, happened. All right. Does it mean all the predictors matter and none should be dropped? Does it mean all the predictors' coefficients are 0? Does it mean at least one predictor has a non-zero coefficient and the model is useful for predicting the response value? Or does it mean at least one predictor has a non-zero coefficient and each one should be tested one at a time? Okay, so let you work on that one. Make sure you got it. All right. And this is, I think, where we were at here. Working through this, talking about this, about running the reduced model. Okay, and here's the next one. Given the following results from running a regression on some data to predict hourly wage for some workers, what predictor would be dropped to run a reduced model? Let's see. Okay, so the predictors are job class, years with company, years in union, or intercept, or you don't need to drop any of these predictors and the model is final. So pause the video again and make sure you understand how to decide which is the predictor you're going to drop. And I believe on this one, I provide an explanation of the right answer. Okay. After you, I think after you submit, I hope. All right. So now we are talking about goodness of fit measures and the standard error of the estimate. So where we're at is for a given sample size, if we increase the number of predictors, it's going to reduce the numerator and denominator. No. Yes. Yes, of course. Yes. The more predictors you have, if in some kind of crazy ideal world where you knew everything that was going on, that we were sweeping under the rug with that epsilon term, and you had like, a million gazillion predictors, you could actually exactly predict Y, right? So the sum of error would go down, but you're subtracting the number of predictors, so that goes down too. So what ends up happening is the net effect allows us to determine if the added predictor variables improve the fit. So what we want is when we're comparing models with the same response, you want the model with the smaller standard error, okay, of the estimate. So that's called the standard error of the estimate. And it's the standard deviation of the residuals, if you will. You want that as small as possible. The next one is the coefficient of determination, and it's given that R squared. It quantifies the sample variation in the response that is explained by the sample regression. It's the ratio of the explained variation of the response to the total variation. And it's amazingly simple to get at. So basically, let me talk you through this. If you're given some data, you're just given a bunch of data, the first thing you're going to do is get the average, right? Get the average X, the average Y. If I give you a specific X, what's the best guess of what is the value of Y sub I? Well, you would use statistics and you'd get the average, Y bar. And how far off would that be from your actual Y? So that's this whole part here, the distance from your point Y. So here's the X, a specific X, right? And it had a specific Y that was observed, and we think they're correlated. We ran scatter plots, and we want to know how far off is just that average right here of all the Y values from that. So it's that difference, right? And the total sum of squares is what is referred to as just how far off every point is from the mean. So we get the difference, each value is from its mean. And if you remember, this looks a lot like the numerator that goes into the variance, the sample variance, and it is. It's what's referred to as the SST. And for each pair of values, x, y sub I, the impossible goal of modeling is to come up with a model that, given xi, predicts yi perfectly for every value of x. So to compare models, we measure how close to this goal a specific model gets and pick the best one. Okay? So, given a pair of values, the corresponding value on the trend line, all right, so we put a trend line in, we call that our predicted, or y hat sub I, is due to the partial effect that xi has, the partial effect of the value of x on y, and it provides a better prediction of y than y bar. The difference between what you get if you use a trend line versus just using, blunt statistics, like basic statistics to get the average, the difference here is what we call the explained difference. And it's explained because we know it fits the trend line. We understand the slope of that trend line, right? And this is our regression equation. And so we call that the explained difference. And that's the basis. That explained difference is the basis of what's called the regression, because it's referring to that sample regression equation. So it's the regression sum of squares. So it's just saying, okay, we know that the mean is not so, not so good, and we're going to get a lot closer. We're going to get this, we're going to explain how far off we are from the mean by getting this difference in here. And as typical, we take those differences and we square them and add them all up together, and we call that the regression sum of squares. For some reason, they put the R at the end. Must be French people who came up with this. They probably say it different in French. I don't know. Anyway, a lot of stuff in statistics was developed by some French people. Okay. So what's left? So now you're at this. You're given an X, your best guess starts out as Y bar. You're like, no, we can do better. We can put a best fitting line. We have this explained. But let's say you still aren't quite to where you observe the value of Y. Well, we don't know why. We just know that there's a gap here. And there's something in our model that we're not accounting for. And so we're off. And that's what we call the unexplained difference. So that unexplained difference is what's referred to as the error sum of squares, or the SSE. And we already talked about that as a residuals, right? So that's the y minus y sub I hat squared. And so when you think about the total variation from a point, from just the average of all the data values, right? So all the data values, whatever they are, we have some average. Right. So the difference between that data and the value y has these two component parts. It has the explained difference and the unexplained difference. And you can do a bunch of algebra and see that the total sum of squares ends up being the regression sum of squares and the error sum of squares. And then once you start with this equation, it's just simple algebra, dividing everything by SST, and then subtracting the one ratio from the one side and rearranging it. And we end up having this ratio right here. And that's what we call the R squared. And that is also called the coefficient of determination. Whoops. And it refers to how much of the variability, because remember, we're doing this for every single X value in our data set. And so we're getting an overall amount, and it's referred to as the amount of explained, or the percentage of variability that's explained from our trend line, a regression equation. Right. So R squared is just SSR over SST, but you can do some fairly straightforward algebra on that, and also get, and I thought I had that in here, I guess it didn't show up. Oops. You can get that the SSE, which is the amount of unexplained variation, sorry, the ratio of SSE to SST, just with simple algebra, is 1 minus R squared. And this is something that we'll use a lot, is that once we know the R squared, because Excel calculates it for us, then we will do 1 minus that to get the amount of unexplained variation. Right, because SST is made up of SSR plus SSE, it's going to always fall between 0 and 1. And of course, the closer that our trend line can hit all the points or come close to them, the better. And that means this ratio will get closer to 1. So the closer the R squared is, the better the fit. Right, so that's the coefficient of determination, R squared. And it quantifies, so that means it just gives it a number, the sample variation and the response that is explained by the sample regression equation. It is the ratio of the explained variation of the response variable to its total variation. Okay. There's a little bit of a problem. Sounds great so far, but we can't really use it for model comparison when you change the number of predictor variables, which is usually what we're doing, right? In this whole step-down procedure, we're dropping one out. So we can't really use it because R squared never decreases when you add more variables. So the more predictors, the bigger R squared is going to be. And you could even, artificially, remember, you want R squared as big as possible, and you can start throwing in things that make no sense. It's going to make your R squared look better. So instead, people came up with this kind of like fix. It's called the adjusted R squared. And what it does is it has this, like, you don't have to worry. I'm not going to ask you to reproduce this equation. I'm just showing you what's under the hood. It's got this like variation on R squared. All this stuff was done to it, basically to impose a penalty for any additional predictors. And the idea is that it enables you to compare the adjusted R squared from different models that have different numbers of predictors. It also has the property that you want it as high as possible. So now you can compare something between different models with different numbers of predictors, and you want it to be as high as possible. Okay? So to select the preferred model, we're going to want to use the adjusted R squared and the standard error of the estimate. And if one model, if the adjusted R squared suggests, like, let's say model 3 is better, but the standard error of the estimate says no, model 2 is better, you usually give preference to the adjusted R squared. And I won't get into all the reasons why, but anyway, it's just given a little bit, it's just considered a little bit better of a tool. These two are kind of tools to decide between models. I meant to get rid of this. Somehow that ended up in my slides. Okay. Anyway, after the preferred model is selected, use R squared to describe. So once we've got the final models chosen, Then we go back and we use R squared because it's much more accurate than adjusted R squared to describe how much variation is explained by the model. Okay, so let's go in and look at this in Excel. All right, so we have this full model, and if we look at this full model, we're going to focus now on these coefficients, and we see that we have one coefficient that's bigger than 0.05, and it's associated with debt. And I'm kind of not surprised because I think that's been kind of a problem. I pointed that out earlier. So we're going to do a reduced model where we drop that. So the way that you'd want to set this up in Excel is this was really kind of bad style, if you will, for doing more serious regression analysis. It's fine if you're doing simple linear regression or what we were doing on Monday, like just trying to learn. But really what we're going to want to do is have another worksheet so we can kind of keep this clear. I'm going to call this the regression models. All right, so in here we're going to put the results from that full model. So I'm just going to copy it and paste it. I don't need to go through all that. I don't need to double up on my confidence intervals either. That's just redundant. I'm going to copy this into this regression models, and I'm going to put it right here. I'm going to call this the full model. All right. Just make some of this a little bit easier to see. All right. We notice, of course, that we already talked about this. This looks good. So now the second thing that I'm going to look at from this full model is I'm going to focus in on these p-values. And I already told you I found one there that is bigger than 0.05. So that's the one I'm going to drop. All right. So my next model will drop debt. Okay. So once so in order to drop debt, I want to run the same this whole model with debt. And I think I have a slide on this. Oops. All right. So we need to restructure the data so that all the predictor data is in one contiguous rectangle. That's a funky thing about Excel's regression tool. So I want to drop debt. So let me go in here and get debt. So here's debt, and I want to drop it, but I'm not going to delete it. I just want to move it because I want cost, grad, and city to be all next to each other. So you can do it however you like to do it in Excel. There is one potential functionality you may not have encountered yet, and that is if you select the entire column at the top and then hover until you get a 4-pointed cross, then hold down your shift key and click on that and you'll get a solid green line and you can move the whole column. Okay, so now I want to run this regression again. So I'm going to go to my tool again, get my regression, and my earnings are going to be the response variable. And then I'm going to put cost, grad, and city. And again, I'm going to use the shift control down arrow key to quickly get that in there. I want to make sure I have my labels so I know what's what. And then I'm going to pick an output range. Now, the other weird thing about Excel is that it doesn't like it if you try to put the output range in a different worksheet. So what you end up having to do is kind of find like a open area and then just cut it out of there and then paste it where your model is. Okay. So here's our new model. Again, I don't care about doubling up on that part. I just want to save a little space here because I'm going to be comparing, so it's just easier not to have to go all the way across. All right, so now I have this new model, and I'm going to compare this reduced model to the full model by comparing. I'm going to be looking at the adjusted R squared to the adjusted R squared here. And we see this one's 4087 and this one's 4062. So the full model's better at this point. And then we're going to also look at the standard error. So this one's, we want that as small as possible. And this is 5,645, and the units don't really mean much, by the way. So don't get hung up on the units. It's just, you want to relate one to the other. So we want the smallest one. So on both counts, the two tools we have to compare these models, the full model is winning here. Okay. And I thought that I was highlighting, but it looks like I was crossing out anyway. So all the p-values are less than 0.05 on this reduced model, right? So we have all these numbers. Remember, the scientific notation means they're really, really, really small. And the biggest one is this 0.03. Usually, once you get all your p-values less than 0.05, this is a good place to stop for now, or stop dropping, okay? I believe in the book, they don't even go down this path at all. I don't know what. Anyway, all right. Then generally we want to create a comparison table of the top 3 model choices and choose the preferred model. Okay, so I think I am going to just go through and show you the results of that without spending a ton of time doing it. So this is what the table would look like. So I'm just going to want you to focus on the one on the left. Okay, so I created this table, and you'd want to create a table similar to this, and all I did was cut and paste from the results. So I just took the regression statistics here and copied them over. So, sorry, my bad. Those are the regression statistics are down here, and then I put the coefficients in the above in the table and what the p-values were for each coefficient, and then I highlighted in yellow which one I dropped. So you can see in model 2 it was dropped, and then off screen I ran a third model where I also dropped city, and so this only has cost and grad, and then I compared the adjusted R squared, and I picked the biggest one and highlighted that, and I picked the smallest standard error. And it's always nice when the smallest standard error and the adjusted R squared are on the same model. Then it makes it really easy to select the final model because they're in agreement. Again, I would give a little preference to adjusted R squared if, let's say, they weren't in agreement. Okay? All right. So once we have that, okay, the final model, which is what we're selecting, explains. Now we refer back to the 0.429, and we can now use that to explain the amount of variability. To state that 42.9% of the variability is explained by this regression model. And if you do 1 minus the 0.429, you get 53.1, and that's the amount of unexplained variability. So you could argue that there's maybe some important variables missing from this data set, like, I don't know, ways of measuring competence or reliability or whatever that could lead to salaries. GPA. There's a lot of stuff missing from that data set. So I'm not surprised that there's a lot of unexplained variability going on here. So go ahead and pause. Well, let me read the question to you. You're going to select the preferred model from those provided in this regression results table. So look over, oops, what happened? There we go. Look over this results table from 3 models and decide based on what you see here, which is the best model. Is it model 1 because it has the largest standard error of the estimate and the smallest R squared? Is it model 2 because it contains important predictors? Or is it model 3 because it has the largest adjusted R squared and the smallest standard error of the estimate? So now I'm going to just touch base about a very important model assumption and common violation, because at this point in model selection, it matters. On the next class, we're going to talk about all the other things you need to think about and be concerned about. But this one really should be part of section 7.2 in a sense, because it drives your decisions as to what you're going to include in your modeling. So there's a list of assumptions, and the second one, and again, you'll get to this on Friday, but the second assumption is that there cannot be an exact linear relationship among the predictor variables. And that is referred to as multicollinearity. And actually, it doesn't even, things get messed up even if it's not exact. So theoretically, if it's exact, it's really messed up. It absolutely won't work. Like the regression just can't handle. Like you'll get an error out of Excel. But if you're close, it still messes things up. So what does it mean? It means 2 or more predictor variables have an exact linear relationship. And if this happens, or even if it's a heading in the direction, you can't pull apart the influences of the one predictor or the other. So what happens is you get imprecise estimates of the slope coefficients. So basically, you can't trust what you get out of the modeling. So it really is a monkey wrench in your modeling, and you really need to look out for it. So in general, the rule of thumb is you look for strong correlations where your R is, the absolute value of R is greater than or equal to 0.7. So either greater than or equal to 0.7 or less than or equal to negative 0.7. That's probably the main way that you detect this. You may also run across a supposed to be an asterisk. Models that just can't be estimated. So you will get a flat out error out of Excel. The other thing that can happen is you can have weird things like a high R squared. So that is looking good. You have a significant F. So overall, you have a significant model, but then you have individual coefficients that are all insignificant. So you're like, how is this possible? So that could be a sign you're dealing with something messed up in the math under the hood because of multicollinearity. Sometimes also you can get the wrong signs of the estimated coefficients. So you expect, based on your scatter plot and the correlation, that you should have, let's say, a positive trend, a positive relationship, but your coefficient comes out negative. Then something happened, right? That's just, there's a problem. Insignificant, important predictor variables is the other thing. So you have a predictor variable really matters, but the regression results state it's insignificant. So the remedy, you have to drop one of the collinear variables. You can't include both of them in the modeling. It's just bad. And then you swap out in the final model to confirm the best choice. Sometimes you have 3 variables that are all collinear with each other, so you have to swap out twice. Basically, you kind of treat them as interchangeable, but they're not exactly, so that's why at the end you always go back and see which of the 3 gives you the best goodness of fit measures. The other thing you can do is obtain more data. You can try and express the variables differently. Sometimes that helps. And You can also do nothing, which I don't really recommend, but sometimes people are required to include certain predictors and they're kind of stuck with it. And if that's the case, you just have to explain what you found. Okay. Well, this one must have had a build by accident. Okay. Sorry about this. All right. So now we're going to address this step in the model selection process that had been grayed out. We're going to identify multicollinearity among predictors. We're going to do that right up front, and that's going to help choose what are the predictors we include in that first full model. All right, and then once we're all said and done, we'll replace anyone. We'll swap them out and see if we get any improvement. Okay, so if I look back at the correlations we got in Excel on that college data, let me go back to that. Sorry, here, we see that we do have a problem between grad and debt. So I'll put that in red because that implies collinearity, right? So we don't trust the correlation coefficient until we graph it. So if I graph that, you'll see it comes debt versus grad has a very high correlation, and the scatter plot indicates yes, it is a linear relationship. So they're definitely in the direction of collinear. They're not exactly, of course, but they are definitely in that direction. So we include only one of those two variables, those predictors in our model. And I'm just going to choose grad as it's just a judgment call. It's just a place to start. So generally, it's important to communicate clearly what are your predictors and which ones are going to get swapped out. So you want to create a little table that says regression predictors. And so the full model, this is before you start, you're going to pick the what ends up being your predictors. So here in the full model, I have cost, grad, and city. And then I indicate which other variables I've discovered are multicollinear that I'm going to swap out at the end. And notice, not notice, but note, if my final model doesn't include grad, I don't have to swap anything out. This is only if the final model has grad. Then I would use debt in its place to see if it improved things. All right, so this is what I'm calling the better model selection logic than what is in the book. And it's better than just doing a full model step down. You really need to check for this because if not, all the decisions you're making along that path could be wrong. Right, so the first thing we're going to do is we're going to only include these three predictors, cost, grad, and city. I see my significance on the joint significance. The joint test is significant. It's a tongue twister. And then I also look at my p-values, and I notice that I don't need to step down. So I don't want you to step down artificially, like I want you to learn good techniques. So if these are all significant predictors, I don't need to step down anything. So I'm basically, my full model is my final model. So the only thing left is this last step right here. And that's the swap out of grad with debt. So I'm going to do that. And remember, in order to do that in Excel, I do need to make sure I have that one contiguous block of data. So I'm going to go back and get debt. And it's probably, let's see, the best way to do this would be to just move grad out of the way. So I could just move that out of the way. And now I have cost, city, and debt. They're in a little bit of a different order than what was there before. I just got to keep track of that. But I can run this regression. And then you can see they're a little bit, well, actually, I redid it in the right orders for the video. Okay. Anyway, so I'm just highlighted in orange to make it really clear when I created my results table. And so I'm showing the coefficients and the p-values. And I see that intercept now is no longer significant, and that's usually one we kind of ignore a little bit. It can be if you, that was the, let's say we had really, really similar adjusted R squared and really similar standard errors, then that could be the deciding factor. So modeling in many ways is where science meets art, and the more experience you have doing this, the more likely you are to make good decisions. But unfortunately, some of this stuff, there isn't like hard and fast rules. So I'm trying to show you all the things you need to be thinking about. Okay, so now that I switched out the model, I swapped out det for grad because they were collinear. And now I compare my adjusted R squared. And I could actually, because I have three, I can even compare my R squared. But just to keep things simple, let's go with what we always do. Compare adjusted R squared and standard error. And in both cases, the original model using grad did better than the one using det. And that leads us to our final model using these coefficients for model one. But it's always good to have a couple or three top models because we're going to also be looking on Friday at other conditions that must be met. So if what you think is your preferred model fails on some of the other assumptions, that then you might have to, start looking for a backup. Okay. One last topic I want to talk about, and that's cross-validation. The goodness of fit measures discussed in this section use the same sample to build the model to assess it, right? So every time we were just running different models on the same data. That doesn't really tell you how well the model does at predicting results from other data or an unseen sample. And the way that this is addressed, and obviously, if you think about it, that's kind of how you want to use the model is on an unseen sample, or, unseen data. So there's something called a cross-validation techniques, and they divide out the original sample. So you have to have a lot of data to even begin to go down this path. And you have what's called a training set, and then you have a validation set. And the validation set is used to provide an independent performance assessment by exposing the model to unseen data and seeing how well it does in that scenario. This is going to be not beyond the scope of our class, but beyond the time limits of our class. So this is an area that if you take other analytic courses, you'll definitely be getting into, but we're going to have to skip it. Okay, and that's it for today's lecture.